Okay, let's continue from. I hope you saw the new syllabus, right? The change of exam dates. So the final exams in the morning at 7:30. I think it's on 5th or something. And then the third exam will be on the last Wednesday before your final exam. Okay. So I'll try and make sure that I grade your exam before the class, which will be on the Friday. Okay. Let's continue from where we left, and we were doing an example on how to prove whether it's linear transformation or not. Okay, so we wanted to look for the range and the kernel here. So we already found the image as C transpose equals to minus C. And this is actually the element of the image of T. The element of the image of T. Now, if the image of T equals to C, which is an element of M by 2 by 2, this element M, which is a 2 by 2, then we realize that CT is equals to what? Is equals to minus C. CT is equals to minus C. So what is the matrix? This is an example of matrix which the transpose, sorry, is a negative, like we can factor out the negative and then you get a transpose. So actually our image, our matrix will be of the form, let's say 0 and then B, then minus B, and then 0 there. Where or B is an element of real number. You look at this, if you transpose this matrix, then it is similar to multiply by transpose, similar to multiply by the negative. Now, therefore, this is the same as we factor out B so that we have 0, 1, -1, and then 0 there, such that B is an element of real number. So therefore, our image is equals to the span of 0, 1, -1, 0. The image of T. What about the kernel? So the kernel, if our A, we let our A to be the element of M, we say this is a 2 by 2. Then for our kernel, then A is actually an element of kernel of T. A is an element of kernel of T. So therefore, then the trans T of A is equals to 0. And this 0 is in what? This 0 is in M2 by 2. It's in M2 by 2. Then it means that this is TA equals to 0 M2 by 2. Then our A minus A transpose is equals to what? Is equals to 0. A minus A transpose is equals to 0. Because we said TA is equals to A minus A transpose. And we say TA to the kernel, then TA is equals to 0 for the solution of that. So then our A is equals to A transpose. Or A is equals to A transpose. So what are the elements in the kernel of T? So then this is the same as so the kernel of T is equals to A, which is an element of M2 by 2, such that A transpose is equals to A, such that A transpose is equals to A. So then what is a matrix in which A transpose is equals to A? A transpose is equals to A. So it is the matrix of the form A, B, and then B, D. So it is actually of that form, because you can still transpose and you still find the same. So for A, B, C, A, B, D to be the elements of real number. A, B, D, elements of real number. So then, how can we write this? So this can be written as, we can factor out A, so it can be written as A 1 0 0 0 plus B 0 1 1 0 plus D 0 0 0 1 for A, B, D elements of real number. So it can actually be written like that. So you can still add it. You can still factor in this A here, this B here, this D here, and you still get then it's A 0 0. When you add the D there, it will still give you. So therefore, the kernel of T is equals to the span of 1 0 0 1 0 1 1 0 and 0 0 0 1 0 0 0 1. So is those are the matrices. Any question up to that?
So it's supposed to be the span of basically the matrix of A, B, D all factored out. The variable, right?
Yeah, actually you're factoring out the real numbers there.
Oh, okay.
So that's the way we were doing in vectors. So factoring out, let's say x1, x2.
Okay, I was just confused because I think there's like an extra one in the first one. It's 1 0 0 1. But the A is 1 0 0 0.
That should be 0. This one should be 0.
Sure, that's what I was confused.
Yeah.
Thank you.
Okay. Let's look at another example. Example number 3. Show that W equals to A, B, C, D. Say that 2A minus B equals to C minus D, and A minus C equals to 2D is a subspace of R4. Is a subspace of R4. So that W is subspace of R4. So as you can see from there, so this W here is actually the solution of homogeneous linear system. So therefore, 2A minus B equals to C minus D, and A minus C equals to 2D can be of the form 2A minus B. Bring this one to this side, minus C plus D equals to 0. And this one is A minus C minus 2D equals to 0. So this W here is a solution of the linear system. So we can say W is the solution sets of the following homogeneous linear system, whereby we have those ones. Now, then, therefore, we can define our matrix A. So we can define A to be equals to, now we take the coefficients of this, and then we form the coefficient matrix. So A will be our coefficient matrix, which will be of the form 2 minus 1 minus 1 1, and then here we have our 1 minus 1, and then we have our B is 0 here. So this is 0, and then C is minus 1, and then D is minus 2. So therefore, so then our W is equal to the norm of A is the subspace R. So since this is the solution of homogeneous linear system, then that means that space of W is the null space of A. Okay. I think we misplaced part of my notes. I'm coming. So let's look at the next section here, which is section 4.3. And this is linearly independent sets. And also we'll look at the basis, the linearly independent sets. So we already defined the linearly independent, but we can still see some definition here. I think I also gave you this one in the first example. So let's look at definition 1.1. We said if we let V1, the vectors, V2, all the way to, let's say, VP, be vectors in vector space, V in vector space, V. Then number one, we say that V1, V2, all the way to VP are linearly independent, if C1 V1 plus C2 V2 plus CP VP equals to 0 implies that C1 equals to C2 equals to CP equals to 0, where C1, C2, all the way to CP elements of real number. You still remember this. For this one to be linearly independent, then it means we have trivial solutions. Only we have trivial solutions. Only. So it means the real numbers there are equals to 0. So it's giving us the trivial solutions only. Now, if it is not linearly independent, then it is linearly dependent. And if it is linearly dependent, then we have the linear relation. So we have the linear relation. Number 2, we say that V1, V2 all the way to VP are linearly dependent if there exists not all 0, C1, C2 up to CP, which are elements of real number. So not all of them are 0. So not all of them are zeros. You can find one of them as linear combination of the other ones. So you find that not all of them are zeros. So if it is linearly dependent, then we have the linear relation. So we have the linear relation. Now, such that C1 V1 plus C2 V2 plus CP VP equals to 0, which is called a linear relation of V1, V2, all the way to VP. So if not all of them are zeros, then we can actually get a solution. So now after getting the solution, then you come and work that the in is also equals. So we'll see an example on that. Okay, let's look at the first examples here. Example number 1. Determine whether the vectors are linearly dependent or not in the given vector space. Determine whether it's linearly dependent or not. So if they are linearly dependent, then get the linear relation. So we can also say if the vectors are linearly dependent, then find the linear relation of these vectors. Number 8. If you have the polynomial P1 of t to be equals to t minus 1, the polynomial of P2 of t to be equals to t plus 1, polynomial of P3 of t to be equals to t squared minus t plus 1, and polynomial of P4 of t to be equals to t cubed plus t in polynomial of real coefficients P3 in the polynomial of this time P. Then determine whether this is linearly dependent. Determine whether it is linearly dependent or not. Now, how should we determine whether this is linearly dependent or not? So what we need to do is we need to write this one in this form, in the form C1, V1, C2, like that, equals what? Equals to 0. So the solution. So here, we determine whether C1 P1 of t plus C2 P2 of t plus C3 P3 of t plus C4 P4 of t equals to 0. Equals to 0. So we need to determine whether that is equals. So therefore, we can now substitute the values of P1 there. So here it will now be C1. P1 is T minus 1 plus C2. P2 is T plus 1 plus C3. P3 is T square minus T plus 1 plus C4 T cube plus T equals to what? Equals to 0. And then now we distribute the seeds C1 and C4. So we open the bracket. So when we open this bracket, then C1 of T minus C1 plus C2 of T plus C2 plus C3 of T square minus C3 of T plus C3 plus C4 of T cube plus C4 of T equals to 0. And then we now collect the like terms. The ones which has the highest power, put them together. The ones with the same power, put them together. So what we should get is C4 of T3, which is this, and then plus C3 of T square plus C1 plus C2 minus C3 plus C4 of T, and then plus minus C1 plus C2 plus C3 equals to 0. So we actually present. So we start from the highest power. The second highest power is this. The next one is T. So you factor out T. So C1, C2, C3, C, then factor out T. And then finally, the constants. The constants are minus C1, which is this. The next one is plus C2, which is this. C3, which is equals 1. So therefore, these are the coefficients. These are now the coefficients. So these are the coefficients. So then C1 equals to 0. C2, which is this one equals to 0, that equals to 0, this one equals to 0, and that equals to 0. So we want to see whether this is giving us trivial solutions only or non-trivial solutions. So then in this case, we now start by putting this one. So minus C1 plus C2 plus C3 equals to 0. The next one is C1 plus C2 minus C3 plus C4 equals to 0. And then our C3 equals to 0 and C4 equals to 0. C4 equals to 0. So then our matrix. So we just took the constant, then we took the next one, and then C3, and then C4 equals to 0. Okay. And then we do what? We write now this E there. So those are what are supposed to. So we now put this one in the augmented matrix form. So in this case, then it will now be The coefficients here are -1. This one is 1. This one is 1. And then the last one is 0. And then this last one here is 0. So 1, 1, -1. Then here is 1, and then 0. Then we have 0, 0, 1, 0, and then the last one there is 0, and then 0, 0, 0, 1, and then 0. Okay. Now, after now doing this, then we now do what? Reduce. So we now reduce this. So make this one to 0. So to reduce that, then it is now R2 will be R2 plus R1. So finally, what you get is -1, 1, 1, 0, 0, 0. And then here will be 2, 0, 1, and then 0, and then 0, 0, 1, 0, 0, and then 0, 0, 0, 1, and then 0. So what can we see from that? So we can see that this one has pivot position, each one, right? So we have pivot position in each and every row and column. So what is the solution? So use what? Linearly. So we have it is linearly independent. So this means it is linearly independent. So therefore, since the homogeneous linear system does not have free variables, we get C1 equals to C2 equals to C3 equals to C4 to be equals to 0. So those constants are equal. So if those constants are equals to 0, so P1 of T, P2 of T, P3 of T, and P4 of T are linearly independent. Linearly independent. Is a constant. Okay, another example would be if we have P1 of T to be equals to T minus 1, P2 of T to be equals to T plus 1, P3 of T to be equals to T cubed minus T, and P4 of T to be equals to T cubed plus T in P3. So determine whether this is linearly independent. So we just do the same way that we've just done. So what we need to do is we need to get C1 P1 of T plus C2 P2 of T plus C3 P3 of T plus C4 P4 of T to be equals to what? Equals to 0. So we now substitute those values here. So C1 of T minus 1 plus C2 of T plus 1 plus C3 of T cube minus T plus C4 of T cube plus T equals to 0. So once you open this bracket and you collect the like terms, then what you should get is C3 plus C4 of T raised to 3 plus C1 plus C2 minus C3 plus C4 of T, and then plus minus C1 plus C2 equals to 0. So you actually collect this like terms. So C3 is this one, then C4, and then the one for T, C1, C2 minus C3. And then the constants will be C1 and then plus C2. Then equals to 0. So we now form the homogeneous linear equations from the constant here. From the homogeneous linear equations from the constants there. So what we get is we can start from the constant here. So minus C1 plus C2 equals to 0. We come to this C1 plus C2 minus C3 plus C4 equals to 0, and then C3 plus C4 equals to 0. Then we do what? We now create an augmented matrix from here. So our augmented matrix will now be minus 1, 1, and then 0, 0, and then 0. We have 1, 1, minus 1, 1, and then 0. And then lastly, 0, 0, 1, 1, and then 0. Now, without even solving this, is this linearly independent? Without even solving, we just look at this linearly independent. It is, right? Because the number of columns here are more than the number of rows. So we say this one is P and this one is what? So if P is greater than 10, then it is what? Linearly independent. So without even solving that, then this is linearly dependent. So the homogeneous linear system is linearly dependent. Now, after seeing that this one is linearly dependent, then we now look for a linear relation. We now get the linear relation. So to get a linear relation, then we need to get a non-trivial solutions here. The non-trivial solutions. So we reduce this one completely to get a non-trivial solutions. So when we reduce this completely, so that means when you reduce R2 plus R1. So you reduce this one completely. So if you You can go solve this one at home. So what you should get is when you reduce this completely, you should get 1 0 0 1 0 0 1 0 1 0 and then 0 0 1 1 0. So that is what you should get when you reduce completely. It's complete.
We have the pivot position here. This one should be zero, pivot position here. Now, so we have our basic variables there.
So basic variable is we can name as C1, C2, and C3, and our free variable as what? As C4. Now, our new linear system here will now be C1 plus C4 equals to 0, C2 plus C4 equals to 0, and C3 plus C4 equals to 0. So then C1 here equals to minus C4, C2 equals to minus C4, and then C3 equals to minus C4 equals to minus C4.
Now, without even doing other stuff, then you can let C4 to be what?
You can just let C4 to be equals to, you can take it minus 1. You can let C4.
So when C4 is equals to minus 1, then C1 will be what?
So C1 will be equals to 1, C2 will be equals to 1, and C3 will also be equals to 1. C3.
So then finally, our
Linear relation there will be C1 P1 of T plus C2 P2 of T plus C3 P3 of T plus C4 P4 of T equals to 0. So we now come and substitute C1, C2, C3 there. So our linear relation is C1 is 1. So here's P1 of T. C2 is 1 plus P2 of T. C3 is 1 plus P3 of T. And C4 is negative 1. So minus P4 of T equals to 0. So
that is how we get the linear relation.
any question up to that?
So this actually applies to the other sections. This actually very similar to the other sections.
Okay, let's look at a theorem here. Theorem 1.2. Theorem 1.2. We let V1, V2, and these are vectors, V3, all the way to VP, be a vector space V. V. Then number 1, and we did this last time. If if V1, vector V1, if one of them is equals to 0 vector, then it is what? This one is linearly dependent. It's linearly dependent. Vector. If you find one vector to be 0, 0, and the others are zeros, or one of them is just 0, then it's linearly dependent. It is linearly dependent. Number 2, if Vk equals to 0 for some k, then V1, V2, Vp are linearly dependent. Now, if one of them, if 1 or 2 or 3 vectors are zeros, just like this, you find that one vector is 0, then it's linearly dependent. Now, if one of them, if let's say k is 1 and it is 0, 0, actually that is a vector. Then from last time we say if we have one vector is 0 and the others are not zeros, then the whole of it will be what? Linearly dependent. And then number 3, if P is greater or equals to 2, if P is greater or equal to 2, then V1, V2, all the way to Vp are linearly dependent if and only if some vector Vk is a linear combination of other vectors. So if vectors that if these are more than 2 vectors, then 2 or 3, then if one of them is a linear combination of the others, then basically it is linearly dependent. Okay, so when we meet next week on Monday, then we look at the basis for vector spaces. The basis for vector spaces.